Today, we are exploring one of the most critical transition in iron making. How carbon capture technologies are reshaping the sustainability of blast furnace steel making. From post-combustion methods to cutting-edge looping systems, this presentation unfold the science, innovation, and potential of CCUS. The steel industry contributes approximately 7 to 9% of global CO2 emission. Of these, the BOF route dominate production, covering nearly 70% worldwide. With carbon pricing, EU Green Deal, and climate neutrality mandate shaping the policy landscape, reducing emission from blast furnace becoming non-negotiable. In a typical steel mill, CO2 emissions arise from several units: blast furnace, basic oxygen furnace, power plant, sinter strand, and coke oven. These streams vary in concentration and volume. Crucially, the blast furnace alone account for almost 70% of total emissions, making it the primary focus of carbon capture efforts. Now coming to our next slide, which is on carbon capture in steel making, which can be grouped into four core categories: post-combustion looping cycle, oxygen combustion combined with top gas recycling, pre-combustion. Each employs different mechanism: absorption, adsorption, membranes to suit various gas types, and furnace configurations. MEA and MDEA are common solvents used to absorb CO2 from flue gases. These technologies are commercially ready and have the highest technology readiness level (TRL 9), but they are costly, with energy penalties ranging from 2.9 to 6.5 megajoule per kg of CO2 and capture cost between 38 US dollar to 204 US dollars per ton. Now coming to the membranes-based system, which separates CO2 by selective permeation. They are ideal for CO2 rich gases like blast furnace gas and basic oxygen furnace gas. These setups are still emerging, with TRLs around 3 to 4 and cost between 35 US dollar to 47 US dollar per ton. So to reach purities above 95%, multi-stage configuration are required. Let us now talk about our calcium looping, which uses CaO to capture CO2 and regenerate CaCO3 through thermal cycles. Chemical looping relies on carriers like Fe or Cu oxides to bind and release CO2. These systems show promising emission reductions up to 75% with experimental success at 1 to 2 megawatt pilot scale. Oxy-blast furnaces use pure oxygen instead of air, enriching the top gas with CO2 for easier capture. When combined with top gas recycling, it saves coke, cuts emissions, and improves furnace control. Energy penalties range from 2 to 8.6 gigajoule thermal and zero point 0.7 to 1.2 gigajoule electric per ton of hot metal. CO2 reduction can reach up to 1270 kg per ton, or we can say it is 1.2 ton, 1.2 ton per ton of metal, hot metal production. Now coming to the pre-combustion part, where pre-combustion methods target gases like blast furnace gas and coke oven gas before burning. Technologies include VPSA and PSA for physical adsorption, ammonia-based chemical adsorption, sorption enhanced water gas shift SEWGS, which combines hydrogen production with CO2 removal purity level reach 90 to 99% with TRL between 4 and 6. Now, this comparison weighs capture cost, purity, TRL, energy penalty, and CO2 reduction. A standout performance is calcium looping for deep reduction, VPSA for energy efficiency, SEWGS for hydrogen synergy and integration. So we can say technologies like pre-adsorption and SEWGS offer excellent reduction at manageable cost. OxyBF alone is less impactful unless paired with capture systems. Overall, cost range between 30 US dollar to 90 US dollar per ton of CO2 with chemical absorption still holding ground as the most mature. Now, most research remains at the simulation and conceptual stage, especially for membranes and SEWGS. Since 2016, interest has grown in low energy capture processes. However, pilot scale studies and economic modeling remains limited, posing challenges for commercial deployment. So we can say that there is no one size fit all solution. Each technology has its trade-off. Successes will depend on strategic integration, reduction of energy penalty, and synergy with renewable energy. Promising path going forward include calcium looping, SEWGS, and VPSA. So we can say that carbon capture is not